You know, shipping has a dirty secret. The ships are drunk. Their engines are filled with alcohol. Massive cargo ships crossing heavy oceans have been running on what's basically leftover sludge from oil refineries. Heavy fuel oil, the stuff that's far too nasty to be put into cars or planes. But for over a century, nobody really cared. It was cheap, it worked, but it was poisoning our port towns and choking coastal communities. So, to fully comprehend why and how alcohol is now being used as a better alternative over heavy fuel oil, we'll have to look at the chemistry involved. When crude oil gets refined, you get different products at different temperatures. The light stuff, gasoline, kerosene, jet fuel, comes off first. Next, diesel, and then heavier oils. That thick, black, tar-like sludge is what's left. It's literally the dregs, the stuff nobody wants. Ships have been burning it since the early 1900s, and it's loaded with sulfur, sometimes up to 3.5% of the weight. Now that might not sound like much, but when you're burning thousands of tons of fuel on a single voyage, that adds up quickly. When bunker fuel burns in a ship's engine, the temperature inside the combustion chamber hits over 1,300 degrees Celsius. At that temperature, sulfur in the fuel reacts with oxygen and forms sulfur dioxides. Some of that converts to sulfur trioxide, which then mixes with water vapour in the atmosphere to create sulfuric acid. You also get nitrogen oxides from the air and fuel reacting at high temperatures, and particulate matter that floats around and gets into people's lungs. The result? Heart disease, respiratory problems, and acid rain. Ships account for about 13% of global sulfur emissions, from an industry that represents a tiny fraction of total vehicles on the planet. So, you see the problem here. In the early 2000s, regulators finally said, enough, clean up or get out. They created emission control areas along the coasts of North America, Northern Europe, the Baltic Sea, and parts of the Caribbean. Basically, ships had to meet stricter pollution standards. The sulfur limit in ECAs, down from 3.5% to 0.1%. That's a 35-fold reduction. With similar rules from the International Maritime Organization, shipping companies were staring down a huge decision. Option 1. Install scrubbers. Basically giant chemical showers. As exhaust gases leave the engine, they get sprayed with seawater or an alkaline solution. The sulfur reacts with the water, forms sulfate compounds, and gets neutralized, or at least captured. Scrubbers add weight, complexity, and maintenance costs. And here's the controversial part. Open loop scrubbers, the most common type, dump that polluted wash water right back into the ocean. You're cleaning the air by polluting the sea. Some ports banned or just ignored them. Either way, they felt like a band-aid, not a real solution. So then we have option 2, switch fuels. But you'd be ditching heavy fuel oil. So what do you use instead? The industry is trying a bunch of different fuels, and each one comes with trade-offs. Liquefied natural gas was the first big alternative everyone talked about. The catch? You have to keep it at minus 162 degrees Celsius. Cryogenic tanks, specialised equipment, and ports that can handle LNG bunkering. Not every port is set up for that. Still, it burns way cleaner than bunker fuel. Almost no sulfur, fewer nitrogen oxides, and about 20 to 25% less CO2. Still a fossil fuel, releasing carbon into the atmosphere, just less of it. Retrofitting an existing ship to run on it would be expensive and complicated. What about hydrogen? Well, on paper, it's perfect. Burn it and all you get is water vapour. Zero carbon, zero sulfur, zero nitrogen oxides if you do it right. So why isn't everyone using hydrogen? Well, for one, producing it cleanly takes a ton of renewable energy. And the reality, most hydrogen still comes from natural gas, which kind of defeats the purpose anyway. Storing hydrogen on a ship is a nightmare. You either compress it to 700 bar, that's close to the pressure at the bottom of the Mariana Trench, or you cool it down to minus 253 degrees Celsius, just 20 degrees above absolute zero. Both options require heavy, bulky tanks, which takes a lot of cargo space and are risky. Then there's ammonia. Compared to hydrogen, it's almost reasonable to handle. You can store it as a liquid at 16 bar at room temperature, or minus 33 degrees Celsius at atmospheric pressure. Way easier than cryogenic nightmares. It's carbon-free, has decent energy density, and can run in modified engines or fuel cells. But, and this is a big but, ammonia is really toxic. A leak in an enclosed space can kill you in minutes. It's also corrosive, so you need special materials for tanks, pipes, and seals. And when you burn it, you still get nitrogen oxides, which means you need exhaust treatment systems to scrub those out. Some companies are testing ammonia-powered ships, especially in short sea routes and ferries. But it requires serious safety protocols and infrastructure that doesn't exist yet at most ports. Methanol. This is the alcohol we've been talking about. Compared to the others, it feels almost normal. It's a liquid at room temperature and pressure. You don't need cryogenic tanks or high-pressure vessels. You can store it in modified fuel tanks, pump it like diesel, and burn it in engines that don't need a complete redesign. It's also versatile. You can make methanol from natural gas, that's grey methanol, not much better than bunker fuel. But you can also make it from biomass or from captured CO2 and renewable hydrogen, that's green methanol or e-methanol. If it's made cleanly, the CO2 you release when you burn it is the same CO2 you captured to make it. That makes it close to carbon neutral, and it's already being used. Most methanol-powered ships use what's called a dual-fuel engine. These engines can run on methanol, regular diesel, or a mixture of both. So why not 100% methanol all the time? Well, because methanol doesn't ignite as easily as diesel. Its auto-ignition temperature, the point where it spontaneously combusts under pressure, is around 470 degrees Celsius. Diesel ignites at about 210. That difference matters in a compression ignition engine, where fuel is supposed to ignite just from being compressed. The engine injects a small amount of diesel first, about 5 to 10% of the total fuel. That diesel ignites from compression, and the resulting flame ignites the methanol. It's called pilot injection. Once the engine is running and hot, methanol takes over and does most of the work. However, one of the big challenges with methanol is that it doesn't pack as much energy as diesel. It has an energy density of about 19.7 megajoules per kilogram, whereas diesel has 45.6. That means you need more than twice as much methanol to get the same amount of energy. So either you install bigger fuel tanks, which eats into cargo space, or you refuel more often. For short sea routes and ferries, that's manageable. You're stopping at ports regularly anyway. But for long-haul container ships or tankers crossing the oceans, it's a tougher sell. Methanol comes with some serious requirements. It corrodes aluminium, zinc, and copper alloys, so tanks, pipes, and seals have to be stainless steel or specially coated. It also absorbs water, so the tanks are filled with nitrogen to keep moisture out and maintain fuel quality. On top of that, methanol is flammable and toxic. Not as extreme as ammonia, but still something that demands careful handling. That means proper ventilation, leak detection, flame arresters, double wall piping, and emergency shutdown systems. The full safety setup. Some ships aren't just burning methanol in engines anymore. They're running it through fuel cells, which generate electricity through a chemical reaction without combustion. First, methanol gets fed into a reformer, which heats it up and reacts it with steam. This breaks the methanol down into hydrogen, carbon monoxide, and carbon dioxide. That hydrogen-rich gas then goes into a fuel cell, usually a proton exchange membrane fuel cell or a solid oxide fuel cell. Hydrogen molecules split into protons and electrons. The protons pass through a special membrane while the electrons flow through an external circuit, generating electricity. On the other side of this membrane, the protons recombine with oxygen from the air and the electrons to form water. All of this outputs electricity, water vapor, a little CO2, and heat. So why does this matter? Traditional engines are loud, inefficient at low loads, and kick out emissions even when idling. Some hybrid ships use methanol engines for main propulsion at sea and switch to fuel cells when they're close to shore or in port. In 2015, Stena Germanica, the poster child for methanol shipping, was retrofitted with a modified Wärtsilä engine that can run on methanol. The conversion cost about $25 million, but it cut sulfur emissions by 99%, particulates by 95%, and nitrogen oxides by 60%. The ship switches between methanol and diesel depending on where it is and what fuel is available. It's been running reliably for almost a decade now. Maersk's methanol fleet, one of the world's largest shipping companies, has gone all in on methanol. They've ordered 25 large container ships capable of running on green methanol, with the first ones already in service. Each ship can carry over 16,000 20-foot containers. So where does methanol fit into the future of shipping? Honestly, it's probably not the final answer, but it's a damn good bridge. LNG, hydrogen, ammonia, batteries, wind assist sails, they're all part of the puzzle. But methanol has something the others don't. It's available now, And it works with existing infrastructure, with a few modifications. And if you make it the right way, it's nearly carbon neutral. So the next time you see a massive container ship pulling into port, there's a decent chance it's not running on oil anymore. It might be running on something a lot closer to the stuff in a bottle of vodka. Just, don't try and drink it. Every episode on this channel takes days to produce, from research and scripting to storyboarding, animation, and even voiceover. And it's all made possible by our Patreon crew. We've just revamped our Patreon and we've prepared a lot more to share with you. As a deckhand, you'll get early ad-free access to new videos, be able to vote on upcoming video topics, grab exclusive wallpapers for your phone and PC, and see your name on our supporters wall at the end of every new video. If you'd like a closer look behind the scenes, the officer tier gives you time lapses of our team working hard on brand new animations or thumbnails. You'll also get behind the scenes updates, animatic releases, and a monthly newsletter filled with maritime stories and news that we don't cover on the channel. And for those who really want to take the helm, our captain tier lets you sail your very own custom designed ship in the casual navigation art style, featured in a future episode for everyone to see. You'll also get your name in the end credits as a captain supporter, with video shoutouts and private Q&A sessions on Discord. However you choose to support, or even if you're just here watching, it truly means a lot. You'll find the Patreon link down below. Thank you for keeping casual navigation afloat.